Okay, as you saw in the last podcast, I suddenly got stopped. I restarted, but then the camera cannot be turned on when that happens, so it's a bit of a pain. So suddenly I disappear, but that's not a big loss. Not that you want to look at me, anyways, right? So let's try to wrap up this particular podcast. We've been looking at marine heat waves and they are also hotspots for impacts on biodiversity and ecosystem services. So we briefly touched on how range, position, and vulnerability to marine heat waves have been documented in previously published studies. I was quite brief in the way these things have been mapped, but you understand the basic process that the species that are able to adapt by moving to deeper depths or to move poleward, they do that, but many of them end up hitting the limits of their distribution. And the idea is that if the species has already moved to the warming that has occurred so far and is just managing to survive with its life cycle, breeding, senescence, juvenile stage, adult stage, reproduction, and senescence, and so on, then another heat wave may just push it over the edge into mortality, right? So these were just the hotspots seen for 2023-24 year from July to June of 23-24, which was one of the warmest periods in recorded temperatures since the Industrial Revolution. Okay, let's continue that with compounding stressors and species interactions, because they tend to modify how the marine heat waves impact the particular habitats and species. So we are looking at numbered items here, so we'll read what they are. The color codes here: bluish colors, kelp and algae 1 to 5. Here again, kelp, fishes and sea urchins. So altered competitive hierarchies here. Herbivory from new species in this range from kelp. So fishes are eating kelp, and algae are exchanging here the competitive hierarchies. And here you have kelp. So this is disruption of the food chains from sea urchins to kelp and sea star to sea urchin. Here you have that's the same thing here as well, but lower trophic levels. So phytoplankton being eaten by zooplankton, being eaten by krill, and then fishes being eaten by mammals and birds. So, as we said, new niches open up and species try to survive by shifting habitats, by shifting prey, or avoiding predators, and so on and so forth, or competition changes as happened here between kelp and algae. Okay, compounding stressors modify MHW impacts as well. So marine warming or marine heat wave effects and river runoffs, which extreme events means massive runoffs, much higher rates than they are used to. Typically the species that live near the river mouths or in the region affected by the river mouth have a certain phenology about when they lay eggs. The eggs cannot be swept away. Larvae need food and cannot be predated too much and cannot be swept away. So there are all kinds of ocean processes that are used for survival. But when you have extreme events on land and you change the runoff, of course we have been changing the nutrient composition of the runoff as well because of fertilizer use, etc., especially nitrogen to phosphorus ratio, which affects the phytoplankton size distribution. So we are hammering the system at all levels, but here we are talking about how MHWs are superposing on all the other natural and anthropogenic impacts. Okay, so kelp and corals are being affected by all these as well. So compounding stressors and species interactions modify MHW impacts. In addition to affecting species thermal performance, as we saw before, marine heat waves also modify direct species interactions such as competition, indirect interactions such as facilitation cascades, and entire communities or ecosystems. They are also called clades, for example. Case studies from around the world, 1 to 21, have documented altered species interaction that have been modified by MHWs, including 2 species interactions such as the competition. So here 1 to 5, 1, 2, 3, 5, and 4 appear in cold waters. So warm waters and cold waters all together. And you have also herbivory, so moving, shifting diets. So red numbers 6 to 9. So you have 6, 7, 8, and 9. So warm waters, cooler waters, and cooler waters. Well, this is the Kuroshio extension, I suppose. So depends on what kind of dynamics there is that supports the food web also, right? 3 to 4 species food chains shown in yellow. So numbers 11 to 15. So 11, 12, 13, 14, and 15. Did we consider 10? Yeah, 10 belongs in the same thing. So 6 to 9, 11 to 15, those must be 10 to 15, sorry. And those involving compounding stressors in teal, so 16 to 21. So you have 16, 17, 18, 19, 20, and 21. This region is highly productive upwelling region, warm Gulf of Mexico region with eutrophication issues. Persian Gulf also generally warm, not so productive. This is a coral triangle, so different dynamics. This is Lewin current, different dynamics. Antarctic circumpolar current, different dynamics, and so on. Okay, so just keep those in mind. Impacts of MHWs on ecosystem services. So maximum MHW intensities 1 to 2 degrees here, 3 to 4 degrees in, 2 to 3 degrees in the yellowish color, 3 to 4 in the magenta color I get, and darker red at 4 to 5 degrees. And ecosystem services include fisheries, aquaculture, tourism, cultural, so dependence on the water for cultural aspects, provisioning, supporting, and regulating, and food security, so heavy dependence on the marine resources in those regions. So you can see marine heat waves affect a range of ecosystem services that provide a wealth of benefits to humans, including commercial and recreational fisheries in blue. So lots of fisheries. Okay, fisheries and recreational fisheries in blue, aquaculture in red, and then you have that those are related to food security as well, as we saw here. And aquaculture, that's red already. Tourism opportunities in green, 1, 2, 3, 4. And a variety of natural contributions, including cultural in black, so 1, 2, and provisioning, supporting, and regulating services in yellow, here only one of them. You have to go and figure out what they are. There is a very nice list of references associated with each. Okay, locations of ecosystem services affected by MHWs are overlain on the maximum temperature of the event. All case studies numbered on the map are discussed in the text. So, oops, sorry. Obviously, this is a meta-analysis which has taken all available examples with some selection criteria to report them. So I will be brief on these remaining sections on future directions, challenges, and solutions. MHWs are intensifying with climate change, posing severe risks to marine ecosystems, biodiversity, and coastal economies. Advances in forecasting and early warning systems provide crucial predictions to help coastal communities and industries to prepare for MHWs. However, challenges remain in detecting MHWs in real time, particularly in remote or subsurface waters where satellite data falls short. So as we said before, just defining MHW needs data to look for impacts is even more stringent in terms of data requirements, because you want to actually attribute the change to marine heat waves. So that's a fairly strict requirement for data. Effective responses require a mix of proactive measures directly aimed at responding to MHWs, such as temporarily adjusting aquaculture practices, and reactive interventions such as species relocation. That's something that always can have unintended consequences, like species not surviving in the new location, or some new invasive species coming along, competitions overwhelming the solution, and so on. Additionally, emerging technologies including remote sensing and genetic analysis and cross-sectoral collaborations offer promising approaches to monitor, understand, and adapt to the impacts of increasingly frequent and intense MHWs. There is more material under this section that I have skipped, but let's jump to forecasting and responding to MHWs, which would be the most interesting topic for me as far as dealing with MHWs. Can we forecast them? If we do, how can we respond to save the ecosystems and biodiversity, ecosystem services, and so on? Improved forecasting systems, early warning models for MHWs, and real impacts on indicator species such as range shifting megafauna, could be big fish like tuna, can help stakeholders to implement proactive management measures to protect vulnerable species, ecosystems, and activities. Yet, detection of MHWs in real time can be challenging and very little predictive capability exists for the impacts. So I've discussed predictability of MHWs in other podcasts already, but then, as I said, attributing the ecosystem changes to MHWs is very difficult. Data collection is typically limited to satellite-based remote sensing of surface temperatures, which can be obstructed by cloud cover, does not reveal subsurface events, and the satellites do not, and satellite data doesn't, and they might not accurately capture water temperatures in coastal regions that are strongly influenced by upwelling or land, because satellites have a certain footprint size which tends to get degraded as you approach the interface of water to land. So some new satellites are trying to address these as well. Moorings and autonomous sensors such as those deployed on gliders can collect real-time data and could supplement the wide coverage afforded by satellites, and real-time observations of sensitive species, including range-shifting megafauna, could provide early warnings. So you call them indicator species, basically sensitive species, because they are able to move, and they can be early indicators that they are moving because something has changed where they were. So then you can go and see what changed, why they are moving, and whether they will survive, and so on, right? Several types of interventions have been attempted with limited success, as they are not universally effective and can face substantial challenges. For example, annual efforts to rescue endangered species can lead to policy fatigue unless companion actions such as preparation of more suitable translocation sites are taken in parallel. There are always issues of territorial waters versus open international waters, where monitoring, verification, and reporting can be very difficult, right? Efforts to pump cool water over coral reefs during peak heat stress would be effective only at a small scale and are not possible nor practical to implement across large areas. There are people trying to do cloud brightening over the Great Barrier Reef, or forming new clouds to try to protect the corals from bleaching as well. Likewise, restoration of marine habitats is still a small scale and resource intensive activity that would be difficult or impossible to implement across the scales of habitat damage caused by MHWs. Over reliance on these emergency responses can be costly and will probably be limited by a small number of species, or limited to a small number of species, or a small area of habitat. These limitations pose a substantial challenge, as management efforts must balance immediate needs with long-term sustainability, thus increasing protection and building resilience into marine ecosystems and urgently addressing climate change, the root cause of the increase in events, rather than relying solely on repetitive and questionable post hoc interventions, is crucial for limiting the impacts on MHWs on marine species, impacts of MHWs on marine species and ecosystem services. A little typo there. What are the challenges to understanding the impacts? Of course, data monitoring, right? Although our understanding of vulnerability to MHWs and the mechanisms behind their impacts on ocean biodiversity is growing, many MHW events remain unreported as vast areas of the ocean contain unmonitored ecosystems and species, as well as thermal conditions that can obscure ecological consequences of these events. So we'll look at a table, but vulnerability is here being used in a very intuitive sense in the real world. For climate vulnerability, typically we have an index with many parameters, like for example, for humans it can be per capita income, the kind of house you live in, your access to health care, gender, education, age. So vulnerability here is just being used in a very intuitive sense without any metric behind it. Okay. In particular, impacts on pelagic and highly mobile species, polar species, long-lived species, and species living in deep water are not well understood, despite reported MHWs affecting these regions and species. Moreover, further research is required into how species and communities are affected by MHWs that occur in colder seasons, during which mortality and altered migration might be less common. These cool MHWs could potentially still have important impacts, such as by affecting recruitment pulses, increasing metabolic rates and energy demands, and modifying species interaction rates. Recruitment, in case you don't know, is basically how many of the larvae or eggs survive into juvenile or adulthood. Okay. Additionally, the effects of MHWs are generally only published when impacts are observed, and often only focusing on specific species of interest, and thus resulting in publication bias and limiting our understanding of ecological thresholds and resilience. Okay. What are the new opportunities for detecting impacts? Advances in technology are unlocking new opportunities for monitoring and understanding biological impacts of MHWs at the temporal, so days to months, and spatial regional scales where these effects are felt. Remote sensing technologies such as autonomous underwater vehicles, gliders, and high-frequency satellite data are transforming observations and responses to MHWs. Although observation capacity must be urgently expanded, many of these tools are already provide continuous, large-scale, and high-resolution data. This enables researchers to monitor biodiversity, temperature anomalies, and ecosystem shifts with unprecedented accuracy and reach. We have a long way to go, but things are only getting better in terms of data platforms, etc. Okay. There is a call that I have to attend to, so give me one. Oops, what did I do? Let me pause. Okay, so that was an important call for my next staying place. But anyway, I was here talking about new opportunities for detecting the impacts. So remote sensing technologies such as autonomous underwater vehicles, gliders, and high-frequency satellite data are transforming observational and observations and responses to MHWs. Although observation capacity must be urgently expanded, many of these tools already provide continuous, large-scale, and high-resolution data, enabling researchers to monitor biodiversity, temperature anomalies, and ecosystem shifts with unprecedented accuracy and reach, and this will only keep getting better. This automation enables the timely detection of MHW impacts on marine species and ecosystems, from population declines to shifts in species distributions. Jumping ahead, although new technology will be instrumental to our ability to upscale detection of MHW impacts, cross-sectoral networks, collaborations, and citizen science also provide powerful new possibilities for expanding our observations. On land, there are various efforts which are using citizen science to enhance the monitoring and logging of impacts at very local scales. Of course, it's not uniformly distributed because you just have some regions where people are very gung-ho about participating in citizen science, and some regions people are not believers in climate change and so on. But nonetheless, hopefully it'll keep growing, especially if you do it at school levels. For example, commercial and recreational fishers and scuba divers are on the water far more often than scientists, and could be valuable for alerting scientists and managers to unusual species occurrences as potential indicators of larger oceanographic anomalies. This could be especially valuable where the capacity for monitoring does not exist. Okay, so let's look at this table then. Knowledge gaps challenging our understanding of marine heat wave impacts on species and ecosystems. Ocean coast mismatch. So obviously coasts are hard to monitor from satellites, resolution issues and transition issues, but also in general you cannot have international teams going into close to the coast and so on. But MHWs are predominantly assessed by remote sensing, and MHW impacts have been recorded in some coastal areas and shelves, but are poorly resolved. So the mismatch challenges our ability to link observed and predicted temperature, stress and impact. So there is further work needed to resolve oceanography on the coast, in the shelf less than 100-meter depth and so on. Long-term monitoring is needed as well, but international efforts will be useful because often the coasts are international boundaries just strung together like a garland. Reporting bias, of course, because it's like a street lamp syndrome. People work where it's convenient or where funding is available sometimes, or where multiple PIs can come together. So it's very common to have biases. So species, locations, biases, as well as there may be places where there is little or no impact, so we may be missing impact hotspots, and rare species may be difficult to observe and so on. So we need long-term biological monitoring data and data sets not originally collected, and these have to include information on multiple species so that you know how the ecosystem is working instead of just one sensitive species. And correlative evidence can be a knowledge gap. Most of the current knowledge of biological impacts of MHWs is based on correlations and unreplicated observations, and little underlying mechanistic understanding exists of ultimate drivers of change. This gap in understanding adaptation, resilience, or vulnerability to MHWs makes separating the relative contributions from different factors during the compound events difficult, challenging attribution and mitigation. So once the impacts themselves are not understood well in terms of drivers, then attribution and mitigation can be a challenge. So undertaking multi-species, multi-factor experiments testing effects of different MHW characteristics on different organismal responses is needed. We need to extrapolate experimental evidence to geographically relevant scales and anticipate MHWs through emerging forecasts and undertake natural experiments. There are also geographic gaps and overlooked biology. For example, impacts have mainly been reported where biodiversity information is available because they are well monitored regions, and for targeted species like fisheries, tourism and so on. Direct effects of temperature such as mortality also dominate the recorded impacts, in contrast to indirect effects and compound effects. So on land, for human beings, we think of not just mortality but also morbidity, which cuts down our performance. You may not die, but you're sick and you're not performing, being productive. What about fisheries, or what about corals? They may not be dead, but are they functioning at some suboptimal level that we can somehow monitor for impacts of MHW. So as a result, understanding of resilience is limited, particularly for long-lived habitat-forming species such as corals, kelps, and seagrasses. So obviously we need a lot of work in these, so expanding scales of observations, undertaking ecological modeling, which is a big challenge without having a lot of data for parameterizing things, and improving modeling frameworks and so on. Maybe AI will begin to have more and more contribution as contributions as we increase the data coverage, because the more data you have, AI doesn't need any physics understanding or biological understanding. It can just hack through data and give you lots of useful information in terms of patterns, trends, correlations, etc. Right? So finally, concluding, increasingly severe MHWs have emerged as threatening and destructive manifestations of anthropogenic climate change in our oceans. Over the past decade, documentation of how MHWs have been at the core of environmental, biological, ecological, and socioeconomic change in marine ecosystems is in virtually all oceans and seas has increased exponentially. All projections indicate that the frequency, intensity, and duration of these extreme events will continue to increase with climate change. The resulting acute thermal stress and increased extreme conditions will profoundly reshape life in our oceans and have profound socioeconomic and environmental consequences into the future. Although reducing greenhouse gas emissions remains essential to address these impacts Although reducing greenhouse gas emissions remains essential to address these long-term impacts, these impacts will be unavoidable and prominent part of the foreseeable future. Closing the current knowledge gaps around MHWs and their impacts on biodiversity, as well as proactive management strategies, are therefore urgently needed to mitigate further damage to ecosystems and people and to build resilience into the future. So again, resilience is also used in a very intuitive sense here, but resilience is basically the ability to recover from a shock, and the recovery speed and functionality can matter, but on land for human systems, resilience has to be that we not only go back to previous functionality, but we adapt to the change that is required of resilience. In other words, it's not the idea of getting stuck where we are in terms of resilience, but make the system resilient so that you become functional, but also address the evolving risks as climate keeps changing and warming keeps happening, right? So keep that in mind. So let's leave this here. It's a nice topic, a little bit long, 30 minutes, but that's okay. It's a really nice topic, even though I've been supremely brief. So you need to go back and read if you need all the details. As I said, a really nice list of references. Okay, see ya.